This video contains the solutions to the circulation and flux practice problems. So all of these problems relate to this curve and this vector field. And for the first couple, we're just looking at trying to use our intuition to see if we can tell whether we think the circulation and then whether the flux should be positive or negative. So in this case, we want to think about whether the circulation is positive, negative, or zero. In other words, to what extent does the vector field push an object, right? Imagine a ping pong ball or a feather or something like that, and imagine that these are wind speeds and directions. So to what extent does the vector field push the feather or the ping pong ball around the curve? So we can see that in this part of the curve, the vectors are pointing generally in the same direction as the curve is pointing, and so we think that in that case we would get positive circulation. But if we continue a little bit further, these vectors are pointing against the direction of the curve, and so we think that would give us negative circulation. For this part here, the vectors are pointing almost perpendicular to the curve, and so again we would think that would give us perhaps zero circulation. These vectors are pointing with the curve, so we get positive circulation. These vectors are pointing against the curve, so we get negative circulation. These vectors are pointing perpendicular to the curve, or close to perpendicular to the curve, and so we think we would get zero circulation there. So we get some positive, some negative, some zero. It looks like in total it might balance out, and so our guess would be that we might have zero circulation here, or certainly a small number for the circulation, perhaps a little bit positive, a little bit negative. So now let's actually compute the circulation. And the circulation here is just going to be the same kind of vector field line integral that we've been doing, f dot t ds. We've got a parameterization for our vector field, so this is just going to be the integral from 0 to 2 pi. This is our standard parameterization, so even though we didn't say it here, since it's the full circle and we've got x being cosine and y being sine, we're going to start here at t equals 0, go around our circle, and end at t equals 2 pi. So 0 to 2 pi. My vector field is y minus x, so that's going to be 2 sine t minus 2 cosine t. And then x is 2 cosine t. I'm going to dot that with r prime, which is negative 2 sine t, comma, 2 cosine t, and integrate that with respect to t. So we figure out our dot product. When we multiply 2 sine t minus 2 cosine t by negative 2 sine t, that's going to give us negative 4 sine squared t plus 4 cosine t sine t. And then when we multiply 2 cosine t by 2 cosine t, we get plus 4 cosine squared t. Since we have even powers of sine and cosine here, we're going to need our half angle formulas. So we get negative 4. This sine squared is going to be 1/2 times 1 minus cosine 2t. 4 cosine t sine t, we can do a simple substitution there. And then for 4 cosine squared of t, again, we're going to need our half angle formula. So that's going to be 1/2 times 1 plus cosine 2t. And then we want to integrate that all with respect to t. So we've got a few simple substitutions here. So here we're going to need u equals 2t. Here we can do u equals sine t. Here we're going to need a u equals 2t. And so we work all that out. And just as we predicted, we do in fact get 0. So now we want to think about whether the flux of this vector field across this curve is positive, negative, or 0. So here we're looking to what extent does the vector field push across the curve. And what we see is that, again, we get a little bit of inward flux and a little bit of outward flux. But the outward flux is these small vectors up here, and the inward flux is these large vectors over here. And then again, we get a little bit of outward flux here. So as we can see, there's much more inward flux to this curve than outward flux. Since it looks like we have more inward flux than outward flux, inward flux is counted negatively, so we think the net result will be a negative total flux. All right, now let's find out if our guess was correct. So to compute flux, we need to integrate a line integral over c of f dot n ds, where n is a normal vector. But again, as we derived in class, the way that we're actually going to do this is to integrate from a to b, and again, we're going to use our same 0 to 2 pi as we did before, of f dy minus g dx. Where the f and the g here, those are the components of my vector field f. So y minus x, that's what I'm calling little f, and x, that's what I'm calling g. And then dy and dx, those are the derivatives of the components of my parameterization. So this is what I'm calling x, as we've done before, and this is what I'm calling y. So f dy, well, f is y minus x, so that's going to be 2 sine t minus 2 cosine t. And then dy, that's going to be the derivative of y, which is 2 cosine t. And then minus g, which is x, which is 2 cosine t, times dx, which is the derivative of 2 cosine t, which is negative 2 sine t. So that's what I'm going to integrate from 0 to 2 pi. Working all this out, what we end up with is 4 sine t cosine t, and then minus 4 cosine squared of t, and then minus 2 times minus 2 is plus 4, times sine t cosine t. And again, we can work out this integral without too much trouble. We can combine the 4 sine cosine t and the 4 sine cosine t into 8 sine t cosine t. So integral from 0 to 2 pi, 8 sine t cosine t. And we can do that integral with a u equals sine t substitution. And then 4 cosine squared of t, we're going to rewrite cosine squared as 1/2 times 1 plus cosine 2t. And we can integrate that with the little u equals 2t substitution. And when we work all that out, we end up with negative 4 pi. Again, a negative answer as we predicted, but that's what we get for our final answer.